So, my name is Gadlicht, and today I'll be talking about how we're using old school statistics, specifically mostly the bell curve I'll be focusing on, and how that's led to a lot of bad science and data science and bad statistics and people being suppressed. But let's go over some basics, and I promise you don't need to know that much math. Okay, so what is the bell curve? And the bell curve, a lot of what I'm be talking about is bell curve specifically, but applies to other normal statistics, they call them, and a lot of other stats. Is the bell curve is unimodal. What that means is there's one big center in the middle where the mean, median, mode, or whatever the measurement you're measuring is. The mean is the average, the median is kind of like the middle number. If you were to order all the numbers, the mode is the most common number. And that there's just one bump. There's not like a 2 bumps or 3 bumps. You don't see anything like bump, 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 bump. Also, in the bell curve, there's no limit. It always can go to infinity or negative infinity. This is a real big problem in data science at times, because if I plot height on the bell curve, I predict there's some people that are going to be 500 feet tall and some people that are going to be negative 500 feet tall. I will predict that. Usually it's such a small level that we just ignore it. And you can do a lot, but there's that problem. It also predicts that it's continuous. Also, like all these statistics almost always look at continuous quantifiable variables. They don't look at categories like something just red, green, or purple. Or if there's can't be or discrete levels like either red or green, you're not some color between. Or if you look at money, oftentimes you might not have something that's a half a cent, or it might just be discrete levels too. There's no black swans, which is when extreme events are more common than you think that they would be by these models. So these tails are more thick. Or there's no feedback loops. So feedback loops often causes a black swan. So a feedback loop could be that as a young kid, I was gifted in something, sports, math, or science. So I received more attention and more training that, which made me even better. And once I got even better, I got even more attention and more attention and more attention. And that made me so much up there. So then compared to average 4, so then I'm a black swan event because how much better I am became magnified. And I'm, instead of being right here, I predict, I'm like all the way up here. And like a lot of people were also with me. Or it could be that someone that had some money as a young child, it got amplified to way more. This actually happens a lot with weather, where more extreme weather events are a lot more common than you would predict. And a lot of people have been pushing the US to update the US models to include more of these events. And that's actually one of the reasons why the US model for weather is a lot worse than the European model, a lot worse. There's also overfitting, that you can fit these models to a data set, and it can fit perfectly to your data set, but it doesn't really work in the real world because you made all these wrong assumptions. And the model is also symmetric, which is not always true. So how are some examples of unimodal being bad? Well, one example is sports. They're not going to work in a lot of sports if you just plot out simply, do people like the sports team or not? Because you're going to have a lot of people that really love a sports team or really hate a sports team. Like they're pretty divided. You might even have a lot of people in the middle. So you might have 2 or 3 bumps. In teaching, it can often occur that a teacher just fits some students a lot better than other students. Maybe that teacher just clicks with some students. Maybe the teacher is sexist or racist or something, or the teaching style just doesn't work. Maybe a style of homework doesn't work for some people. Maybe some kids have a lot more resources because they're born into a better part of the neighborhood or richer or something like that. Maybe they're just more interested, so you could see big one. Or you can look at test scores, like oftentimes there's 2 bumps when one kid didn't study. You have 1 bump for the kids that didn't study, 1 kid for the bump for did study. The kids that did study will have a higher bump than the ones that didn't. Or you can look at it with ND diversity, which is neurological diversity or neurodivergence diversity, or however you want to say it. And typically people start talking before 1 year of age. Between 1 year to 1.5 year of age they start talking. But a lot of neurodivergence with autism start talking after 3 years old. Or I had a teacher that played a bunch of music, which she showed studies that helps the average kid. But for me, it was super distracting and I couldn't focus. I know most people learn advanced language skills first, but I learned advanced math skills before language skills. And when you use any of these methods, you get rid of these minority bumps. These bumps are smaller, or you get rid of the diversity. Instead, you make a bump somewhere more in the center. It's really bad also for rare diseases, because when you have a rare disease and you have a drug that only works for like one person in a rare disease, it kind of gets exaggerated and you can stop seeing it because, it just doesn't work for small sample sizes. And exaggerates it, so if it doesn't work for both people, if it works well for one but it doesn't work well for another one, you can get it that it doesn't work well for both and disappears. And that's a huge problem between rare diseases, is even miracle drugs for one kid will not get approved, and it happens more often than you think. But a huge one is actually medicine for men and women. Huge problem. For some medicines, stimulants, these are generalizations, stimulants tend to be a lot more powerful in male and biologically male ones, and depressants tend to be a lot less powerful. And the opposite is true for females, that depressants tend to be a lot more powerful and stimulants are a lot less powerful. You can kind of see it with caffeine and alcohol. But and there's a bunch of other drugs, this causes a huge problem in that the center is actually a lot closer when you put the center of men and women, a lot closer to men. So men usually get a lot more optimal doses of drugs than women. And with Luneta and a bunch of other sleeping medications, women oftentimes get way overprescribed the dosage, and this has led to a lot of females, and I apologize for saying women, I should be saying female. This has led to a lot of females getting way too much high of a drug overdose. This has led to cases of many of them being hospitalized and even deaths. Then when they slightly make it less, male people don't get as much. It's also even worse because in drug trials, there's actually males tend to be taller, heavier, and females tend to be shorter and lighter, but we get more males because I'll show you later on, the distribution, the average distribution is close to the male side. So study, by not looking at multimodal distribution, we get mostly males in studies, and that can mean that a study can be over 80% male. The Obama administration tried to fix this, then it was destroyed by the Trump administration. There are other reasons for this gender gap in medicine. It also includes employment. Not only is not the math fucked up, but it's also that plenty of females go on and then they just randomly get rejected. So this is more on how, and it should say male and female, and I apologize if I make that mistake. Is that when you look at height distributions, males tend to be more spread out. This means the average is actually closer because of how they spread out to males than female, which tend to be more peaked. So more males are closer to average, which is what they usually want in a study. They want the average, most people to be around the average. And that leads to oversubscription of males in studies. And it leads to also the females in studies being unusually tall or unusually heavy and other things like that. This too much this leads to people when they use this data, they get too confident that they have the right answer, when oftentimes they don't. In psychology, we oftentimes get rid of outliers because we're using the bell curve, and then but the outliers turn out to be important. And I've gone to discussion with a professor and multiple people about development psychology, because they got rid of everyone that was an outlier, then built a theories on the normative people. They were like, advanced language skills are necessary to develop advanced math skills. And language precedes math, and they used a bunch of data, but they got rid of all the outliers and they used a small sample size. And I'm looking at them like, my math skills really are developed, and I know other autistics like me way before my advanced language skills. I was doing calculus before I could properly read most books, and I had really bad speech. This is not common, but it's not too uncommon in autistics. And yeah, it's language skills do not always develop. And I said that I think you need some sort of abstract thinking either language or math or space or some other way, and that can translate into thinking in other ways. And then people translate differently, but they know. And that's because they got rid of the outliers with the bell curves and to make the data neater, which makes them overconfident. In economics, it can be way overused because you predict that everything follows this nice pattern when there could be a lot more bumps, and it does, and you get rid of all those bumps or fluctuations, which might be inherent to it, and you get way more prediction powers. Who's not to say that some guy gets up with him that it would make it, for example, it makes rich people look less rich, it makes extreme poverty disappear. You get more people clustered in the center. You also don't see as diverse groups, like you don't see that certain racial groups might be discriminated and have a lower average. So racism, sexism can seem to appeal other disadvantaged groups that might be in the data, or you don't see that the data fluctuates more than it does. So here are some alternative models which I'll go over. So one way of looking at this with an alternative model is random forest and feature importance. So an idea in a random forest is I have a bunch of, so feature importance you can do without random forest, but I'm going to use random forest to illustrate it, and I'll go without feature importance. I take a bunch of data and I randomly split it up into a subsample. So this is my random subsample. This subsample, I then take it and put it into a tree. And a tree works. In a tree, I choose one random variable, and I use this random variable to split up the data into the best I can with a simple fit. And I have one side have more blue, and one side will have more of the other color. And I do that again and again. And I keep doing that. And then I choose another random sample and make another tree where I split up the data better and better into smaller pieces until I only have one type. I can then use this to figure out how important a feature is in predicting something. And how important a feature is in predicting something is called a feature importance. This has a couple of really major, random forest especially has a couple of major advantages. So I talked way back about overfitting. So let me get back to overfitting. Overfitting is when if I put more and more variables into my data to control it, which is a common method with bell curves and stuff, I can easily make the data fit my model. Very easily. If I have 10 data points, but I have 10,000 variables for each, I can fit any curve. If I have 10, like just easily, almost perfectly, if you have more variables times the amount of data points, If that's more than what you're trying to predict, you will always fit the curve. And then there's a good chance if you have even less. But this doesn't do that, because at each step, I only look at one variable, the most important, and I do this many, many times with the subsamples. So I see if anything is actually particularly important, or is everything a tiny bit important? In which case, it's probably just due to chance, and I can measure that. Is it just due to chance, or is it something that in every tree is important? And the more variables I stick in, the more that these trees will just they're going to fit first to the simplest, then the more complex they get. And they always get really complex, I know it's not working. If they stay simple, there's only a few variables that come out, then I can predict it. And again, unlike the other methods with the bell curve, the more variables I get, the more likely I can see if something is actually important with the amount of data I have, which is amazing. And because I choose a random sample each time in these trees, and I have many trees, and each time I look at a random sample, I can fit super complex curves, and so this mathematically, I can fit curves that are not normal with bimodal, or have as many modes as they want, and I can still measure how important they are in predicting it, because they're just how well any one variable how one variable appears so many times in a one. And to make it even more accurate, I usually only put 60% of the data in or less, and then I test it with the remaining data to see if it still works on data that I even didn't make the model for. And this really can accurately tell if something is important, future importance. However, the problem with future importance is that future importance is not the nicest, in that it doesn't tell me directionality. It might tell me that height is important, but it doesn't tell me is tall important or shorter important. That I need to make other models afterwards. But it's nice, it starts off with the simplest model, splits every variable with a simple line at each step, like this line, which they use SVM here, but display models, and it's random, so there's no bias sampling for each of the little trees. And again, with future importance, the more variables, the better. And you can also find clusters of data, so you can use it to figure out what you should cluster with. Is there clusters are centered around men, or is there clusters centered around women, when one of them is pulling out? And it can work with discrete variables, and there's even ways to cat boost with categorical variables. You can feed this into something called a Gaussian mixture model once you know what's important to find more complicated distributions. So what is a Gaussian distribution model? Well, I saw a Gaussian mixture model, GM. So a Gaussian mixture model, here are some pictures of it, but a better Gaussian mixture model, also here, is that it's like the bell curve, but instead I can use more variables. So I have one variable plot, instead of having just one variable for x, I can have two x's. I can have the probabilities with height and how much people are with height, and I can have weight. I can also have multiple peaks, because I generate a bunch of different bell curves that can have mobile variables, and each of them have different centers and they can overlap. So these are actually two different bell curves made from two different variables and the probability of each. Here you can see it with three different ones. And this is where I can start making better predictions. That's one thing that future importance can feed me the right parameters into this model so I don't overfit. And this model, I can also figure out how many clusters I need when there's not too many clusters or too little clusters. With enough clusters, I can fit any data. So the future importance tells me what data to look at, what variables, and the clustering methods we can look at is like the elbow methods one, where this is how good it fits, and well, distortions how bad it fits, and this is how many clusters there are. When it stops being a big improvement, I stopped making clusters. That's one way that's done. Because after that big improvement, after it stops, it just makes tiny little improvement. You're just moving around a little bit, and you're probably overfitting actually. You're probably not just fitting to the data, not to the real world, and you want some flexibility, so you want to just capture the big ones. The other one is a silhouette method, where I look at, there's a peak, and I only use the clusters in the peak. And the silhouette method looks at number of clusters here and average silhouette width, which is how much close it is compared to the user method for silhouette is how well everything fits within to its closer cluster point compared to every other one. And when you get more clusters, it starts averaging fitting better to every other one because the other clusters are also closer together. It's more dense. Like if I have 500 clusters here, it will also be an average closer to one of the clusters. There will be a cluster right here, very close. If I have two, then it's going to be more spread out, but each cluster is not going to work as well. Those are two often methods used to find the optimal amount of clusters. But still, the best one really is to use logic and a good sample size. Good samples will always overcome anything, any fancy statistics or anything. And logic, you have to think, does your model have a problem? Does something not make sense? A lot of studies have had really bad samples, especially I've shown this in like psychology. Is some bad ones examples in psychology are that there was the marshmallow test. They used to hear was like the test where they would give very young kids marshmallows, and the marshmallows they would see how long they can wait before eating the marshmallows, and the longer they wait, the more likely they get a reward of another marshmallow, they would tell them. They found that kids that waited longer were a lot more successful later on in life, had high IQ and all this stuff. But they only looked at, what happened though was they only looked at white, rich families that employed their kids into it from wealthy countries. When they repeated the study in Africa, in poor neighborhoods, they found the opposite. Which is, you sound very weird, but the reason why you could conclude the opposite is maybe those kids were used to waiting longer and being more patient, and it was more the rebellious kids that made it well in their lives, where another kids that showed perseverance, and the rich kids were more likely spoiled, or something like that. The sample was biased. There's other studies in there's all these studies in beauty and stuff about what's the ideal person, how the ideal person looks. They were very, very, very messed up, and they only varied one parameter at a time, and they found like the best hip ratio, the best bust ratio, best height ratio. Turns out actually it's a lot more diverse because they only looked at white male heterosexual college students, which is usually what's employed, all from the West. And then they also only let you vary one parameter at a time, which meant that you find the ideal for one, then you match it to another one. But if you allow to vary more parameters randomly, people start diversifying, and oftentimes people would have multiple ideal ones, or we start from different points, and the whole science was bogus about what people found looked the best. It also turns out they would use the Unimodal one, so if there's an average, but a lot of people don't have the average. So that's like bad samples. Another one is bad logic, is that they looked at people lying, and people lying with pop psychology has been fully based on anxiety, because the idea is that you're more anxious if you're lying. However, they did not think about, well, what if someone has a traumatic thing? And I've seen this in the real world. If you have trauma and you're having a panic attack or something traumatic happened to you, you have all the signs of panic. You're fidgety, your memory's messed up, your speech is messed up, you might get details wrong, so you might have trouble with eye contact. They also did not look at neurodivergence, like autistics that have eye contact problems oftentimes. They also didn't look at some of the best liars, let's now get away, because those people can lie calmly, and or people that believe in their lies. So, yeah, still we need logic and good samples, but be careful with looking at all these data and statistics and really criticize how they were studied and what the model actually means. Thank you very much.